Most of the equations we look at involve two variables, x and y. Here we're going to look at something called parametric equations, which introduces a third variable and allows us to express both x and y as functions of that variable. To understand why these might be helpful to us, let's think about a rider on a Ferris wheel. In particular, let's think about a rider on the London Eye, a 135-meter tall Ferris wheel that rotates about once every 30 minutes. If we imagine the y-axis going through the center of the Ferris wheel and the x-axis lying along its base, then using what we know about circles, we can write an equation for the London Eye. That equation would be x squared plus y minus 82.5 all squared is equal to 67.5 squared. This uses the radius at 67.5 and the fact that the London Eye sits about 15 meters off the ground. We could use that equation to help us figure out the location of a rider. If we knew how high they were on the wheel, we could figure out how far to the right or left of center they were. Alternately, if we knew how far to the right or left of the center of the wheel they were, we could figure out how high they might be. In other words, the standard equation we use for a circle represents the relationship between a rider's horizontal and vertical distance from the origin. What if we wanted to ask a different question, though? What if we wanted to understand where the rider is on the wheel at a particular time? This seems like a reasonable question, given that we know how fast the wheel is moving. However, our typical Cartesian equation, the one we see here, does not involve time at all, and so won't help us answer the question. In order to answer this question, we need to introduce the variable of time and figure out how x and y depend on it. If we let x equal 67.5, the radius of the wheel, times the sine of pi over 15t, pi over 15 because the wheel turns 2 pi radians in 30 minutes, and we let y equal 82.5 minus 67.5 times the cosine of pi over 15t, we can use those equations to determine where the rider is at any given time t. This idea of introducing a third variable, called a parameter, and using it to rewrite x and y in terms of it, is the big idea behind parametric equations. We are using parametric equations when we define a curve by two functions, x equals f of t and y equals g of t. I'll note here it doesn't have to be t, but t is the most common parameter you'll see. And then as t varies, the point x of t, y of t traces a curve. Parametric equations have direction. The direction of the trace we see as t increases is called the positive orientation of the curve. Let's look at an example so we can understand these ideas a little bit better. Let's start by making a graph for the parametric equations x equals t squared minus 1 and y equals t plus 1. The most straightforward way to do this is to make a table of values. We'll choose some select t values within our interval, and we'll figure out what are the x and y coordinates that correspond to that. So let's look at t is -2, -1, 0, 1, and 2. That should be enough points to give us the general idea of what the shape of this is. Notice that when t is -2, x is -2 squared minus 1, which is 3, and y is -2 plus 1, which is -1. When x is -1, we get 1 squared minus 1, and y is -1 plus 1. When t is 0, we get 0 squared minus 1, and 0 plus 1. When t is 1, we get 1 squared minus 1, which is 0, and 0 plus 1, which is positive 1. And when t is 2, we get 2 squared minus 1, and 2 plus 1. This transforms into a set of points if we just look at the xy coordinates. 3, -1, 0, 0, -1, 1, 0, 1, and 3, 3. These can then be plotted on a set of axes, just like we normally do in the Cartesian plane. So I'm going to plot the points 3, -1, 0, 0, -1, 1, 0, 1, which, look at that, that should have been a 2. 0, 2, and 3, 3. And we can see that our curve looks something like this. But now we have to remember that this has direction. So we're going to examine the orientation of this. The positive orientation is the direction that we move, that our points move as t increases. So notice that we started at this point right over here, 3, -1, and then we move towards the left to get to 0, 0. So our orientation goes this way. And we continue from 0 to 0, we went to -1, 1, and so on and so forth. And so those arrows mark the orientation of our curve. Now you probably noticed in that last example that our curve looked like a very familiar parabola that opened to the right. And so this leads to the question, can we rewrite parametric equations in the more familiar Cartesian form? And the answer to that is yes. What you're generally going to do is try to use some relationship that you know about in order to relate the coordinates to one another, or, as in this case, solve for t. So here, since we have that x is t squared minus 1 and y is t plus 1, notice that if we solve y for t, we get that y minus 1 is equal to t. We can then substitute that in to x to get that x is equal to y minus 1 squared minus 1. If we multiply that out, we get y squared minus 2y plus 1 minus 1, or x is equal to y squared minus 2y. We have to remember, though, that our original curve was only defined for values of t between -2 and 2, which means that we're going to need to restrict x or y in this case in order to not generate a larger section of the curve than we originally intended. But notice that given that -2 is less than or equal to t is less than or equal to 2, if we add 1 across here, we get -2 plus 1 is less than or equal to t plus 1 is less than or equal to 2 plus 1. But t plus 1 is exactly equal to y. So we can see then that we now have that -1 is less than or equal to y is less than or equal to 3. And so if we restrict our graph to the values of y between -1 and 3, we will get the same curve. Let's look at another example where solving for t, like we did in the previous one, isn't going to be particularly helpful. Here we have that x is 3 times the cosine of t and y is 3 times the sine of t. If we solve this, we get that x over 3 is the cosine of t, so that t is the inverse cosine of x over 3, which if we plug in here, we get this equation y equals 3 times the sine of the inverse cosine of x over 3. Not super easy to graph. However, we do know that the cosine squared of t plus the sine squared of t has to equal 1. That's the Pythagorean identity. If we multiply everything through here by 9, we get that 9 times the cosine squared of t plus 9 times the sine squared of t is equal to 9. But notice that 9 cosine squared of t is the same thing as 3 cosine of t squared, which means that we can write that term as x squared. Similarly, notice that 9 sine squared of t is 3 sine of t all squared, so we can write that term as y squared. And so we get that this is x squared plus y squared equals 9. That is Cartesian, and this is a circle with radius 3, and its center is at the origin. We have one last thing to consider. Remember that in our original equation, we had t between pi and 2 pi. When that's the case, 3 cosine t and 3 sine t are only on the bottom half of the circle. So what that tells us is that for our new graph, our y values have to be less than or equal to 0. Our x values will cover the full range from -3 to 3, but our y values will only be the bottom half of the circle with radius 3, and therefore they will have negative components. Now, much like we did for the Ferris wheel early on, sometimes we want to take a Cartesian graph and we want to consider motion along it by parameterizing it according to time. So let's see if we can parameterize this equation. We have the simple parabola y equals 2x squared plus 4. And x is the values between -1 and 5. One really straightforward way to do this is to just let x be equal to t. If we let x be t, then y becomes 2t squared plus 4. And then because x went from -1 to 5, we could just let t do the exact same. Not all of our parameterizations will be that straightforward, but we do have some general rules that can help us to do this. For instance, if we want to parameterize a line and we know that the line has a slope b over a, and we know one point on that line, x naught, y naught, we can use the parameterization x equals x naught, the starting point, plus a times t, and y equals y naught plus b times t. Let's use that in an example now. Let's see if we can parameterize the line segment that starts at the point 2, 3 and ends at the point 4, 7. So we know we're going to use something of the form x naught plus a times t and y naught plus b times t, where b and a come from the slope. So if we're connecting the points 2, 3 and 4, 7, the slope of that line is going to be 7 minus 3 over 4 minus 2, or 4 over 2, which we can simplify to be 2 over 1 if we want, or not. We can leave it as 4 over 2 as we want. It turns out that the parameterization is not actually unique as long as we're using some multiple of the slope. Let's use the point P, which is 2, 3, as our x naught, y naught. So that's going to tell us that x is then 2 plus 1 times t, because remember a comes from the denominator of the slope. The slope is of the form b over a, and that means that y is going to be 3 plus 2 times t. Now, we only want to carve out the line segment. Here, if we don't restrict t, this line is going to go on forever in both directions. So since we start at the point 2, 3, when we want it to be there when t equals 0. So let's just check that what's happened. When t is equal to 0, we get that x is 2 plus 1 times 0, and y is 3 plus 2 times 0, which means we are in fact at the point 2, 3, which is where we want it to start. Now, we don't know when t should end, but we know that when t is at some value, we'll call it e for ending time, then x is 2 plus e, and y is 3 plus 2e, but we also know that we want to end at the point 4, 7. So in other words, we need 2 plus e to equal 4, and we need 3 plus 2e to equal 7. Well, the first equation gives us e equals 2. And if we check that here, 3 plus 2 times 2 does in fact equal 7. So we know that our ending time has to be 2. So what we see then is that our final parameterization is that x is 2 plus t, and y is 3 plus 2t. And we're going to restrict t. T starts at time 0 when we're at point P, and t ends at time 2 when we've made it all the way over to point Q. Wrapping up what we know, parameterizations allow us to redefine curves as sets of points of the form x of t, y of t, so that as t varies, those points trace out the curve. The parameter t controls the motion and direction of the curve, and these can be useful in representing curves that can't easily be expressed in the form y equals f of x.